Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So basically this is a continuation of lecture video for chapter 3, which is induction machines. Okay, alright, so my name is Dr. Nur Zulali binti Muhammad. So this is my email address, so you can just feel free to email me whenever you have a question regarding the content of this video. Alright. So the topics that we are going to cover in this video is include the power flow diagram for the induction machines. Okay, so for the power flow diagram, the input to the induction motor comes from the three-phase supply. Okay, and then the secondary winding of an induction motor is shorted, so no electrical output will be exist. Instead, the output will be in mechanical form. Okay, the power flow diagram for the induction machine is shown as per below. So in order to understand the power flow diagram that's shown here, we need to refer to the equivalent circuit of the induction machines. Okay, so here you have a input supply. Okay, so will be your motor input. Alright, and then whenever you have a resistor, okay, here you also have a resistor, here also you have a resistor. So there will be a losses or in terms of the heat in the winding. So that's why here from the input power supply, there will be losses in terms of PSCL, or we call it as a stator copper losses. Okay, plus the iron losses, PC. Okay, so PC is for iron losses, PSCL is for stator copper losses. Okay, so the input supply minus the losses here, so you are left with the air gap power, or we call it as a RIP, Roto input power, or we can call it as a input that go to the roto side. Okay. Alright, and then in the rotor part, there will be also a losses we call as a rotor copper loss due to the R2. Okay, R2 will cause the rotor copper loss. So the air gap minus the PRCL, so you are left with the P mechanical. Okay, mechanical power, which is your PM. Okay, and then again, because the rotor is a moving part, okay, compared to the stator, you know that stator is a static part, but rotor is a rotating part. So the rotor might have another losses that we call as a windage and friction losses due to the rotation of the rotor. Okay, so the PM minus the windage and the friction losses, which is we call it as a P mu, will be equal to the motor output, which is your P out. Okay, alright. Okay, so the PFD, the power flow diagram, can be normally represented as a fishbone as well. Okay, so again, if you refer to here is the input to the power because we supply the three-phase supply to the motor. Okay, and then you are going to have a losses due to the R1 and also the RC. So you are going to have PSCL and also the PC. And then the input power, you minus with the PSCL minus with PC, you are left with the P air gap, or we call it as a rotor input power. Again, due to the R2, you are going to have a PRCL. This is the losses at the R2. Okay, so the P air gap minus the PRCL, so you are left with the PM. PM we call as a mechanical output. Okay, and then due to the rotation of the rotor part, so you are going to have a P mu. P mu is the friction loss or windage, okay, due to the movement of the rotor. So the PM minus your P mu will be left with your P out. So this is your electrical output. Okay, so if you refer to the fishbone, this branch 1, 2, 3, and 4 indicate the losses happen in the induction machines. Okay. Okay, so this diagram represent the other way on how you interpret your power flow diagram. Okay, so you can start with the input to the motor, which is your P in. P in will be equal to 3 IV cos theta. Okay, and then there will be a losses in terms of core loss and also copper loss. Okay, so this is due to the R1, this is due to the RC, and then your input power minus these two losses, so you are left with the P air gap. Okay, so the formula for the P air gap is given by, because the P air gap is essentially the power that across the R2 divided by S. So that's why you can use the formula 3I squared multiplied with R2 divided by S. Okay, so this is the formula for the P air gap. Okay, again at the rotor part, okay, there will be losses in terms of R2. Okay, losses at the R2, we call it as a rotor copper loss. So the P air gap minus your rotor copper loss, so you are left with the PM. So this is the formula for PM. Okay, And then you are going to have a mechanical losses as well as stray losses. So this one we call it as a P mu. Okay, so P mu, so Pm minus your P mu. So you are left with your output power of your induction machine, which is Pm minus your P mu. Okay, alright. So this is another way on how to interpret the power flow diagram as well. Okay, so here you have a stator part. Okay, here you have a rotor part. As you know, the stator is actually the static part that does not moving at all, and then here is the rotor part that move. Alright, so first of all, you are going to put your rotor inside your stator. Okay, so the input that go to the stator is actually the input power, which is P in. Okay, and then due to the winding in the stator part, so you are going to have stator copper loss, and then you are also going to have the iron loss. Okay, so this is your PSCL, this is your PC. Okay, and then the output that left, meaning that the input power you minus with your PSCL, you minus with your iron loss, so you are left with the RIP. So RIP is the rotor input power. So meaning that this is the active power that we really supply to the rotor part. Okay, and then due to the winding in the rotor, you are also going to have PRCL, meaning that this is the rotor copper loss. Okay, and then the RIP minus your PRCL, so you are left with the PM. So this is the mechanical output power. Okay, but you know, since the rotor is a moving part, so you are going to have a windage and also friction loss, which is your P mu. Okay, so finally the PM minus the P mu, so you are left with the P out, which is your shaft power, or we can also call it as a output power. Okay, alright. Okay, next, this is the equivalent circuit of your induction machines. Okay, so based on the above equivalent circuit, we can obtain the power equations such as follows. Okay, so first of all, this is the input power that goes to the induction machine. So the input power can be given by the formula of Z3 multiplied with V line multiplied with I line cos theta. Okay, or it will be equal to 3 E phase multiplied with I1 cos theta, provided your circuit is your motor has a star connected configuration. Okay, and then for the PSCL is actually the losses that due to the heat dissipation at the RS or R1. So that's why the formula that you can use is a P equal to I squared R, because it is 3 phase. So that's why you have 3 multiplied with I1 squared, because the current that go through the RS is I1. 3 I1 squared multiplied with your R1 or RS lah. Okay, alright. And then for the PC is actually the power that the heat that dissipated at the RC. So the formula is given by P equal to 3 V squared divided by R. So in this case, your voltage across here is equal to the E phase, or the voltage in term of phase. Okay, so 3 multiplied with E phase squared divided by RC. Okay, and then for the PRCL is actually the heat dissipation that come across the R2. So that's why you can use the formula of PRCL equal to 3I2 squared R2, because here the current is I2. Okay, not I1. Here is I1. Here is I2. 3I2 squared R2. Okay, and then for the PA gap is actually the power that goes into the rotor side. Okay, so the formula is given by 3 multiplied with the current, which is I2 squared, multiplied with R2 plus R2 multiply with 1 minus S divided by S. If you further simplify these two equations, you can get R2 over S. Okay, and then the PM is happen here. Okay, so that's why PM is equal to 3 multiply with I2 squared multiply with R2 multiply with 1 minus S divided by S. Okay, so this is the PM, mechanical output. Okay, and then for the P out will be equal to PM minus P mu. P mu is actually the windage losses or the stray losses. Okay, alright. And then by substituting all this equation, you can actually obtain this several formula. Okay, so you just need to memorize this formula. So basically your PM, here is my PM. If I substitute my equation of from here to here, so I can get the PM will be equal to PA gap multiplied with 1 minus S, or PM will be equal to PRCL 1 minus S divided by S. Okay, and then the input to the rotor, or the rotor input power, can also further simplify from here. From here you can further simplify it as a PM divided by 1 minus S, or RIP is equal to PRCL divided by S. Okay, so these two equations you must try to memorize in order to do the analysis later. Okay, and then in terms of the efficiency of the motor is given by the output power divided by the input power. Here is the output power divided to your input power. Okay. So next, for the torque equation, okay, so the general equation for the torque is given by torque equal to power divided by omega. Okay, so this is the general equation for the torque. Torque equal to power divided by omega. Okay, or you can further simplify it as a 60 multiplied with power divided by 2 pi n, where n is your speed, okay, and then P is your power in terms of watt. Okay, so for the mechanical torque, or we can call it also as an induced torque. So since you know this is the general equation, so the P here you must replace with the PM because it is for the mechanical torque, so you must use PM. Okay, and then for the omega you must use omega R, which is the speed of the rotor. Okay, because when we measure the mechanical torque, it is based on the PM that we measured at the rotor side. So that's why we are going to use the speed of the rotor. Okay, so the formula is given by mechanical torque is equal to 60 multiplied with your mechanical power divided by 2 pi and R, speed of the rotor. Okay, for the output torque, okay, output torque same goes with the mechanical torque. Since you are going to calculate the output torque, so that's why you must use the P out. Okay, here mechanical torque you use PM, but here when output torque you are going to use P out. Okay, and then for in terms of the speed, you are going to use omega R, which is the speed of your rotor. Okay, for the starting torque, okay, so this is the formula of your starting torque. So in the case of starting torque, basically the S value is equal to 1. Okay, and then you just memorize this formula lah later for use. Okay, so this is the starting torque. Later on in the next slide, you are going to see what does it mean by the starting torque. Okay, for the time being, so you just need to memorize the formula. Okay, and then next for the maximum torque, so this is the equation that given for the maximum torque. Okay, where during the maximum torque happen, the formula for the S max is given by this equation. Okay, alright. Okay, now let's have a look at the following example on how to solve the problem that related to the power flow diagram. Okay, so the question here, you have a 8-pole 3-phase 50 Hz induction motor that run at a speed of 710 RPM with an input power of 35 kilowatt. Okay, and then the stator copper loss at this condition is equal to 1200 watt. So this is a PSCL. Okay, while the rotational losses are 600 watts. So here is your P mu. So first of all, you need to find the rotor copper loss, your PRCL. Okay, and then you need to calculate the mechanical power developed, which is your PM. And then finally, you need to calculate the mechanical power output, which is your P out. Okay, so the solution for this question is actually first of all, you can rewrite all the parameter given. Okay, so the pole equal to 8, frequency 50, the speed of the rotor is 710, input power to the machine is 35k, the PSCL is equal to 1200 watt, and the P mu, the rotational loss, is equal to 600. Okay, so first of all, you need to calculate the rotor copper loss. Okay, so firstly, you calculate the speed of your NS, which is your speed of your synchronous speed. Okay, so NS equal to 120 F divided by P. So 120 multiply with your frequency is 50 divided by your pole is 8, so you get 750 RPM. Okay, so based on the NS, then you can find your slip. So S will be equal to NS minus your NR divided by NS. Okay, in this case, your slip is equal to 0.053. And then next, in order to calculate your PRCL, we refer to the power flow diagram in terms of the fishbone here. Okay, so Pin is given. You are going to find the PRCL here. Okay, and then the PSCL also given. Okay, so the formula that you can get, first of all, you need to find your P air gap. Okay, so the P air gap will be equal to the P in minus your PSCL minus your PC. Since in this question, it does not give you the PC, so it can be assumed neglectable. Okay, so the P air gap will be equal to P in minus your PSCL. So 35k minus 1200, so it will be equal to 33.8 kilowatts. So this is the P air gap input to the rotor. Okay, so for the PRCL, Okay, you can use this formula. PRCL will be equal to the slip multiplied with P air gap. Slip is given by 0.053. So finally you get PRCL, the rotor copper loss, is equal to 1.8 kilowatt. Okay, alright, next for the mechanical power developed. So you are going to calculate the PM here. PM, you can use the formula of PM is equal to 1 minus S multiplied with P air gap. Okay, so just now in the previous slide, you know P air gap is equal to 33.8 K. And the 1 minus S, 1 minus 0.053 multiplied with 33.8 K. So you are getting the mechanical power developed is equal to 32 kilowatt. Okay, and then finally, the mechanical power output is the P out. Okay, P out will be, if you refer to the power flow diagram here, P out is equal to PM minus your P mu. Okay, PM is 32 kilowatt minus your rotational losses is given in the question is 600 watt. Okay, so finally the P out is equal to 31.4 kilowatt. Okay, alright, so that is how you do the analysis of the induction machine by using the power flow diagram. Okay, so next we go to the example 3.2. Okay, so the question here, you have a 7.5 kilowatt, 440 volt, 3-phase, star-connected, 50 Hz, 4-pole squirrel cage induction motor that developed full load torque at a slip of 5%. Okay, so the question gives you the value of S when operated at rated voltage and also the frequency. Rated voltage and rated frequency. Okay, so the rotational losses include the core, windage, and also the friction are to be neglected. Okay, so the P mu is neglect, the PC also neglect. Okay, so the motor impedance data is given as follow. Okay, your R1 is given by 1.32 ohm. Your X1 is equal to X2 prime is equal to 1.46 ohm, and XM is equal to 22.7 ohm. So by using the Thevenin equivalent circuit, okay, so this question are going to use the Thevenin circuit, find the value of R2 prime. So you need to find the value of R2 prime based on the data available. Okay, so here you can draw first your Thevenin equivalent circuit. Okay, so this is the Thevenin. You have a input is a V Thevenin, and then your R1, XM, and also your R1 and also your X1 is given is replaced by the R Thevenin and also the JX Thevenin. Okay, and then for the rotor part, you just redraw it again. So you have R2 prime divided by S here, JX2 prime. Okay, alright. So given output power is 7.5 kilowatt, the V line is 440 volt, and then S is given 0.05. So this is the value of R1, X1, and also the XM. So based on this value, these three value, 1.32 ohm and 1.46 ohm, and also the XM, you need to calculate the value of R Thevenin and X Thevenin first. And also you need to calculate the V Thevenin. Okay, so this is the formula for the V Thevenin, and this is the formula for the Z Thevenin. Alright, so for the I2 prime, you can just use your Ohm's law. Okay, you can just substitute the value of voltage supply and all the impedance, all the equivalent impedance to get the I2 prime by using this formula. Alright, so again, you need to calculate the V Thevenin, R Thevenin, and X Thevenin. Okay, first of all, you need to calculate your V1 first. Okay, since the question gives you in terms of the 3-phase supply, the V line is 440, so you need to divide by square root 3 in order to get the V phase. Okay, V1 is equal to 440 divided by square root 3. So V phase or V1 is equal to 254.03 volt. Okay, and then just use this formula to get the V Thevenin. Okay, so you just substitute all the value accordingly. So finally you get the V Thevenin is equal to 238.327. Okay, so next we need to find the value of R Thevenin and also X Thevenin. Okay, so this is the formula for the Z Thevenin. You just substitute all the value accordingly, the value of R1, X1, okay, XM, and then finally you get the Z Thevenin is equal to 1.162 plus J 1.435 ohm. Okay, alright. So once you know the value of this, and also this, then you can find the value of R2 prime here. Okay, alright. So this is the Thevenin equivalent circuit with all the value of V Thevenin is equal to this. Okay, and then the value of R Thevenin, and here is the value of X Thevenin. Okay, so this is your power flow diagram for the induction machines. Since the rotational losses, which is your core, windage, and also friction, are to be neglected, Okay, so your P mu and P RCL is to neglect. So you can assume your P out will be equal to your P air gap. Okay, so the formula for the P air gap is given by 3I 2 prime squared multiplied with R2 prime divided by S. Okay, because the P air gap is actually the power that go to the rotor side. Okay, so here the equivalent R will be equal to R2 prime divided by S. The current is I2 prime, so that's why here I2 prime squared. Okay, and then after that, you know the equation for the I2 prime is given by this equation. From the previous slide, you can see the I2 prime will be equal to this equation. And then after that, you just substitute all the value accordingly. Okay, so you know your P air gap is 7.5K. And then you have your V Thevenin, you have your R Thevenin, you also have the value of S. Okay, X Thevenin also you have. And then for the x2 prime is given by 1.46 given in the question. Okay, S is 0.05. Okay, so you are left with only with the parameter of R2 prime. Okay, so in this question, the question asks you to find the value of R2 prime. Okay, so we just further simplify the equation. So we get the quadratic equation. Okay, so this is the quadratic equation. Then you just use your calculator. Solving by using the calculator, you get the R2 prime is equal to 0.995 ohm and also 0.024 ohm. Okay, so usually we are going to get the bigger value, which is R2 prime is equal to 0.995 ohm. Alright. Okay, so next we go to example 3.3. So the question here, you have a 3-phase 280 volts. So this is the V line to line. 50 Hz, 20 horsepower, 4-pole star-connected induction motor, runs at 142 RPM. So this is your NR. Has the following parameter in ohms per phase referred to the stator. Okay, so you have R1, R2 prime, X1 equal to X2 prime, 0.25 ohm. Okay, and then you have a XM. So in this question, the rotational losses is considered to have to be 400 watts. So 400 watts, so this is the P mu. Based on the IEEE equivalent circuit, okay, so you need to use the IEEE equivalent circuit. You need to determine the motor current, and then you need to determine the I line. Okay, so you need to determine the stator copper loss, the PSCL, the air gap power, the rotor copper loss, PRCL. Okay, and then you need to determine the shaft power. Okay, so what does it mean by shaft power? Shaft power is actually the output power. And then you need to calculate the developed torque and also the shaft torque. Okay, so for the developed torque, it is based on the P mechanical. P developed is a P mechanical, and then the shaft torque is based on the shaft power. Okay, and then after that, you need to calculate the efficiency of the induction machines. Okay, so let's see on how to solve this question. We go to the next slide. Okay, so first of all, before you start your calculation, you need to calculate the value of the speed of the synchronous speed, okay, the slip, the omega s and also the omega r lah. Okay, so again, you just write down the parameter given again. Okay, so the ns is given by the formula 120 multiplied with your frequency divided by pole, 120 multiplied with 50 divided by 4, you get 1500 rpm. So this is the ns. Then based on the ns and also the nr given, you can calculate the value of S, your slip. Okay, slip is equal to 0.05. And then for the omega S is given by 2 pi ns divided by 60. So you just substitute all the value accordingly. And S is given by 1500 rpm divided by 60. So the omega S is given by 157.08 radian per second. And for the omega R, just substitute the value of NR in the formula. Then you get 149.23 radian per second. Okay. And then next we go to the question number 1, where we need to calculate the line current. Okay, so we just refer back because the question asks you to use the IEEE equivalent circuit. So this is the IEEE equivalent circuit. So remember, for the IEEE equivalent circuit, we didn't move the magnetizing branch, we just leave it there, but we remove the RC. Okay, so this is the equivalent circuit. Right? And then you need to find the line current. Line current, in this case, we refer to the I1. Okay. So, you know the E phase, E per phase is actually given by the V line to line divided by square root 3. So, in this case, V line to line is 280 volt divided by square root 3. So, you get the E phase, which is your V1, is equal to 161.7 volt. Okay. And then, in order to find the line current, which is I1, you can just use the Ohm's law, where I will be equal to voltage divided by the Z equivalent. Okay, so for the Z equivalent for the IEEE approximate circuit, so first of all, you know that this element, which is the JXM, is parallel with these two impedance. Okay, so the JX2 prime plus your R2 prime divided by S is parallel with the JXM. Okay, so you try to simplify it, you get the Z0. Okay, so Z0 is given by 1.84 plus J 0.6 ohm. Okay, so this 2 is parallel with this, and then after that the Z0 here, the Z0 is in series with the R1 plus JX1. Okay, so the Z total, which is your Z equivalent, is equal to Z1 plus Z0. Okay, so in this case R1 plus JX1. Okay, you plus with the Z0. Okay, 1.84 plus J 0.6. So finally you get the Z total is equal to 1.96 plus J 0.85. Okay, so once you get your Z equivalent, the equivalence, so the Z equivalent for this circuit, you know your V1, and then you can find your I1, which is your line current. Okay, so I1 will be equal to the voltage divided by the Z equivalent. So the voltage is given by 161.7 volt divided by the Z total. So finally you get I1 is equal to 75.7. Angle is negative 23.4 ampere. Okay, alright. Next, the question asks you to calculate the value of stator copper loss here, right? So the formula for the PSCL is given by 3 I1 squared multiplied with R1. Okay, so in this case, you know from the previous slide, you have the value of I1 already. I1 is actually the line current that you get from the question number 1. So you just substitute accordingly. And then finally, you get the PSCL is equal to 2.06 kilowatt. Okay. Next, for the air gap power, okay, we refer to the power flow diagram. We know the P air gap is equal to the input power minus with your PSCL. Okay, so provided your PC is neglected, because we are using the IEEE equivalent circuit, so we remove the RC, so that's why you don't have PC. Okay, so in this case, your P air gap is equal to P in minus your PSCL. Okay, so the input power, the P in, is given by square root 3 multiplied with IL VL cos theta. So you just key in all the value accordingly. So you get the input power is actually equal to 33.7 kilowatt. Okay, so the P air gap now is 33.7K minus your PSCL, which is 2.06 kilowatt. So you get the P air gap is 31.6 kilowatt. Alright. Okay, so next for the roto copper loss. Roto copper loss is the heat dissipation happened at R2. So you can use the formula of PRCL equal to S multiplied with your P air gap. So just substitute all the value accordingly. You get PRCL is equal to 1.58 kilowatt. Okay, for the shaft power is actually your P out. Okay, P out, you refer to the power flow diagram. You get P out is equal to PM minus your P mu. Okay, so PM you can calculate based on the heat dissipation at this. Okay, so PM is, or you can also use the formula of PM is equal to 1 minus S multiplied by P air gap. So this is the value of PM, the 30 kilowatt. Okay, and then just substitute this value into here. Okay, P mu is given by 400. PM is given by 30K. So finally you get the shaft power, which is your output power, is equal to 29.6 kilowatt. Alright, next we are going to calculate the developed torque and so shaft torque. Okay, so for the torque, the general equation is given by power divided by omega. Okay, so in this case, because the developed torque and so also the shaft torque happen at the roto part, so that's why we are going to use the omega R. Okay, so torque developed equal to the mechanical torque is equal to mechanical power divided by omega R. Okay, you just substitute all the value accordingly. You get 201 nanometer. Newton meter. Okay, and then for the shaft torque is based on the P out. Okay, divided by omega R. So just substitute the value. You get 198 Newton meter. Okay, so finally, the last question is the efficiency of the induction machine. For the efficiency, the formula is given by P out divided by P in multiply with your with 100. Okay, P out in this case is P out here 29.6K divided with your P in. P in is given by 33.7K. So finally, you get the efficiency is 87.8%. Alright? Okay. So I think that's all for now. Thank you for your time. Thank you for watching my video. I'll see you in my next video. Okay? Bye.